Okay, we're going to be doing a TripleO deep dive on the deployed server feature in TripleO. Feel free to interrupt me at any time. This is, not a super structured presentation or anything. I was just going to run through how we've been using this feature in our CI since Newton, how we then moved on and productized that with some improvements for the Okada release, and then kind of show some of the things I've been working on in Pike, which is really just a set of patches at this point. It's not been merged upstream yet, so I'm kind of looking for some feedback on that. And it's kind of, how you would make use of this deployed server feature to kind of deploy a split stack in TripleO. And I'll get more into what I mean by split stack later when I get to that section. So first off, when I say deployed server, I know not everyone will know what that means, but what it basically is it's a way in TripleO for us to configure OpenStack services on servers that have already been deployed and provisioned outside of Heat's knowledge. So Heat actually does not use Nova or Ironic to provision these servers. They've already been provisioned by some other tool. And the whole point of the feature is to kind of allow people to use their existing provisioning tools, whatever they might be. It could be something like Foreman, or Cobbler, something that's Kickstart based, or it could even be some virtualization tools, that are not Nova. So things like Overt or something like that. However, these systems are provisioned. What this deployed server feature allows you to do is it then kind of allows you to wire up those systems into the TripleO deployment, so that we can then start orchestrating the services part of the deployment on those servers. And kind of the first place that we were able to make use of this feature was in our CI. So upstream of OpenStack infra, they have the ability to kind of spawn multiple nodes per CI job. And then when they hand over control of the CI job to your project's scripts, in our case, that's TripleO CI, you have access to, however many nodes you requested, whether it be 2, 3, or 4. And you can then kind of test with those pool of nodes, however you want to. So we started making use of this in Newton to kind of scale out our CI. And we've been able to test a lot more scenarios than we were able to do with OVB previously, because we had a lot more capacity. Because OpenStack Infra, they actually talk to 8 or 9 different clouds, so they have a lot more virtual capacity than we do in our RH1 OVB cloud. So I was just going to show how some of that is hooked up right now. Well, first, before I do that, let me just kind of show the original way that this worked. So this is kind of the original patch that myself and Steve Hardy kind of worked on to enable this feature in TripleO Heat templates. If you're familiar with kind of Heat and the resource registry and the way it works with environments and whatnot, what we're able to do is, if I bring up in this patch the resource registry environment, you can see what I did in this patch was I mapped a new resource type, OS TripleO server, and that's mapped to the built-in resource OS Nova server by default. So this mapping just provided an abstraction for OS Nova Server, but by default, we maintain the same behavior. And then if you actually wanted to use deployed servers, you would use this environment file, where you can see that OS TripleO server is actually mapped to a nested stack. And let me show what that nested stack looks like. So, when you replace a built-in resource in heat with a nested stack, you have to provide the same interface via parameters that map to that resource's properties. So that's kind of what I've done here. This set of parameters is the same set of properties that are on the OS Nova resource, or the OS Nova server resource. And then basically all I'm doing is I'm just creating a software config resource. And what that allows you to do is once you have this software config resource, which is really just represented as a unique UUID in heat, you can start associating deployments with that resource. And by deployments, I mean something like this script here, or later on when we run our Puppet steps, those are also software deployments. So you can associate those with this software config resource. And then externally, you have to configure these deployed servers to kind of pull heat for the metadata that is associated with this software config resource. And then it will start pulling these configs down from heat like this script, and it will execute the script locally, or it'll apply the Puppet manifest locally, or whatever the deployment might be. All right, so that's probably a little confusing, just kind of from a high level. So I'll kind of get into kind of how we're using this with CI. So first off, if we kind of jump into the project config repository, which is where all of our CI jobs are actually configured. Inside this repository, there is a node pool directory, and node pool is the upstream project part of OpenStack infra that is responsible for spawning a pool of nodes that are available, that can be given out and assigned to different CI jobs. So if you pull up the nodepool.yaml configuration file, which I must already have open somewhere else, but who cares? So we have a set of images here. What I'm looking for is right here. So yeah, so these node types, this one's called CentOS 7.2 node, and it's based off of the CentOS 7 image. And this subnodes :1 just means that you get one node as part of the job by default, and you have one additional subnode. So that will give you 2 nodes total for jobs that use this node type. And down here, this is actually the list of clouds that support this type of node. So we actually have 11 clouds that can spawn a 2-node CentOS 7 job. CentOS 7 3-node job, and we even have a CentOS 7 4-node job, although we don't yet have any actual CI jobs in TripleO CI that use 4 nodes. We do have a 3-node job. So this is just kind of where the generic node definitions are defined if you're interested in how that part works. So if we jump back up, oops, still in project config, but if we go into the Jenkins jobs and look up the projects.yaml file, this is where all of the actual CI jobs are actually defined. And this file is quite large. I'm already at the location where the TripleO jobs are defined. Yeah, we have a lot of jobs. But kind of starting here, all of our jobs are kind of tied to the TripleO CI repository. It's just kind of easier that way. You can tie your CI jobs to any repository you want, but it's kind of easier for TripleO to define them all in one place. And then your jobs have a node type associated with them. And so let me find the I think the current multi-node job is like feature set 004 or something. So that's the one I was going to try to show. Yeah, there it is. Okay, so this particular job is named CentOS7 non-HA multinode OOQ, and the type is multinode, well, arbitrary string. And then our scripts kind of parse this string and know what type of job to run. But this is the part that ties back to the node definition in the nodepool.yaml file. So we're saying here that this job runs on a CentOS 7 2 node configuration. That's pretty much it for that. So if we jump over to TripleO CI, if we pull up the kind of the entry point for all of our jobs, it's actually tokigatetest.sh, which is now a symlink to tokigatetest.ooq.sh. So we'll pull that up. And there's a little case statement here, which basically sets some variables based on the job type. But essentially, this is where you end up in the script if you're running a multi-node job. So this is kind of the part that I want to talk about. The rest of the script is, it's not too complex if you kind of read through it, but it can be a little daunting kind of the first time you open the file and see all the logic in here. But if you're running a multi-node job as opposed to an OVB job, this is where you're going to end up. You're going to end up down here in this else clause. So we do a little bit of prep on the main node first, which is also called the primary node, and that's the node that we're going to use as the undercloud. So we're just kind of generating some SSH keys and cleaning up some old packages that were installed. This is kind of significant to multi-node jobs. We actually create a dummy image. So you can see here, we're just creating a 1 gigabyte over cloud full.qcow2 image. And this is because, since we're not using Nova and Ironic to actually deploy these nodes from images, they're already deployed. However, TripleO Heat Templates has some built-in constraints that kind of make sure images exist in Glance. So we kind of have to create this dummy image and load it into Glance anyway. So that's the reason that we do that. That's actually fixed in master. We've been able to disable those constraints, but we still do it here just for backwards compatibility since these CI jobs run on multiple branches. Not too much more interesting down until we get to about this part here. What we're doing here is we're calling into TripleO.sh -- bootstrap subnodes. And what this is going to do is it's going to run a script on each of the subnodes, and I'll go ahead and bring that up. It's going to run this script on each of the subnodes to kind of prepare them to be part of a TripleO overcloud deployment. So we have to install some initial packages and make sure that things like EPEL aren't installed, and this Python request part here is actually because for some reason this is installed by pip on the standard image, so we need to fix that up, and we clean off old Puppet stuff. Some of the stuff in the script can actually be cleaned up now because it's no longer required, but it doesn't hurt to do it anyway. We make sure all the packages are updated, and then this is really the main thing you have to do if you want to tie in a deployed server to a TripleO deployment, is you have to install the heat agent packages on each of the deployed servers. So we're installing Python heat agent splat, which just it gets you all the agent packages, because they're kind of packaged separately. There's one for like the script deployment, Puppet, Docker, etc. So we just go ahead and install them all. But that's really the main thing you have to do, is make sure that those agents are installed. That's it for the bootstrap script. And then we start running Toki quickstart.sh, which I will show that. So this just defines the quick start commands that are going to be executed based on the variable set in the previous script. It's not too much logic going on here, really. We just kind of build some commands and then we call quick start. So at this point, things kind of just start running in a typical TripleO CI job fashion. Quick start sets up repositories on the undercloud. It builds an undercloud configuration. It installs the undercloud. Obviously we're not doing things like node registration and node introspection because none of that kind of makes sense in a multi-node job. And all that's controlled by the Ansible tags in quick start. And we even get all the way up to the point to where we start to deploy the overcloud. And kind of once the overcloud deployment starts, it starts creating the software deployment resources to configure the nodes. And at that point, what you have to do on each deployed server is you have to go and configure the previously installed agent to actually start pulling heat for that job. And I have a deployment up that I wanted to show what that looks like. If I can find it here. Yeah, here we go. So this is just an undercloud that I've got deployed. And I've actually already deployed an overcloud, but what I want to show you here is just the configuration that you need to pull out of the heat resources. And then you use that configuration to individually go and configure each of the deployed servers. Kind of the difference here is that when you're not using deployed servers and those instances are launched by Nova instead, this agent configuration is actually automatically injected by the Nova user data. However, since we didn't use Nova to boot these nodes, we have to inject it manually. Of course, by manually, I mean you could do it. You could use a separate script to do it, or you could use Ansible to do it, or something like that. but it can't be done automatically by heat. So let's just take a look at the resources in our stack. Should have sorted that. All right, so we have a resource group here called controller. I'm going to list the resources in that stack. We're just deploying a single controller in this case because it's a non-HA job. So I'm going to list the resources in that stack. And then this pulls you down into where you can actually see the nested stack for the server resource. And here we see we have a resource called DeployedServer. I'm going to show the metadata from heat for that resource. Okay, well that was quite a lot of data, but luckily what we want is right at the end. So this is a huge JSON dictionary of all of the metadata associated with this server, and the metadata is things like what software deployments need to be applied to this server. So if you want to run scripts on the server or something, the actual contents of that script would be embedded in this JSON dictionary. But also part of the metadata is this OS collect config configuration. And so we're saying under the OS collect config key, we are configuring the request collector to use this metadata URL. And this is what we need to manually configure on the deployed server so that it can pull back to heat. Just wanted to show everyone real quick that if you were to manually curl this URL, you're going to see that exact same. Let me try that again. You're going to see that exact same metadata from heat if you curl this URL. So, that kind of gives you an entry point back into heat from anywhere on how to get this metadata. So let me just show you how that is configured on the overcloud node. Subnode IP address is actually in this Etsy node pool subnodes file on the underclass, so I can just SSH to this. Now I'm on the node I intend to use as the overcloud, and in the agent configuration file, I have that same URL in here. So again, I've already run this job to completion, so it's already configured. But if you're going to do this manually, you would, you could type out the contents of this file, or you could use Ansible template, or something like that. What we actually do in TripleO CI is we use a script to do that. So let me show that. And that is in the TripleO heat templates repository. And it's just called get OCC config. OCC just stands for OS collect config. If we pull that up, this is about 120 line bash script, so it's not too bad. But yeah, this should probably be Ansible by default. This is kind of something that we need to move to Ansible. I think it'd be a little bit cleaner. But basically, this script as input takes a list of your role names. I've got the default role names already in here, and it takes a list of IP addresses. And what it's going to do is it's going to kind of query heat. You can see I'm running some stack resource list commands, basically those same commands I just showed in my terminal. basically saving the outputs of those. And down here, I'm querying for the deployed server metadata URL. Then I have a little snippet here, which is the actual OS collect configuration. And then I SSH to each IP address and copy that configuration down there, or onto each node. Start the service and make sure it's enabled. At that point, the agent is going to start polling that metadata URL. It's going to see that it's got new software deployments available based on what it pulled in from Heat, and it's going to start deploying those locally. And it's going to start signaling back to Heat as well that it's completed these software deployments. And then Heat is going to continue moving on in the stack, creating the rest of the deployments. And if everything works, it'll run to create complete. That's about it for CI. Oh, that's right. There's one other bit that is kind of interesting from the CI perspective. So let's see. Just thinking about how to explain this clearly. All right, so when you install an undercloud, everyone's probably pretty familiar with the fact that you have to choose a subnet CIDR to use as your provisioning network. And from that subnet, we're going to be allocating ports, which are associated with an IP address to each of the nodes in the deployment. Well, when you're using deployed server, the same thing still applies, even though we're not actually doing the actual node provisioning. We still need a network that we can allocate ports from. And so you can see in this example, I've got a control plane network just as if I was going to use Nova to deploy nodes. And it's associated with the default CIDR of 192.168.24.0, which is the default CIDR we use in TripleO by default. And I've even got ports allocated from that subnet. Now, all this is important because when you're running these TripleO CI jobs on different public clouds, most public clouds are configured in a fashion such that you can't really just route whatever IP traffic you want to out of your instance. There are firewall rules in place that basically say, oh, hey, only traffic originating from this IP address, which is the IP address that I know I've assigned to this instance, is allowed out. And that's done for various security purposes. So, you know, when we go to assign something like the control virtual IP to an overcloud node, it's not going to be, you know, no other node is going to be able to reach this IP address because of the infrastructure that we're running on. I wouldn't be able to ping this IP address from the undercloud, which would be a problem. We wouldn't be able to finish the deployment, and we wouldn't be able to have an HA overcloud, obviously, if none of the nodes could talk to each other. So how do we work around this issue? Well, what we do is we basically tunnel the traffic through a VXLAN tunnel that is set up in Open vSwitch. So I've created a bridge on the undercloud here called VREX, and there's a port on this bridge, which is a VXLAN tunnel. And these are they're just called options in Open vSwitch, but this is the data associated with the tunnel. So the local IP address is 192.168.0.13, which is the private IP actually assigned to me by the host cloud. And then the remote IP address is 192.168.0.16, which is the IP address of my subnode. And basically gives me a route to where I can route the 192.168.24.0 traffic across BREX. And that traffic is going to go through the VXLAN tunnel to the remote IP address. That overcloud node is going to then see that, hey, you're trying to ping the control virtual IP, and it's going to respond and route it back. So that's basically how that works. It's a little complicated, probably, if you're not fully aware of the networking stuff. But thankfully in TripleO CI, all of this will be set up for you. And also, if you're just running locally, like if you're just using deployed servers locally that were kind of deployed on like some vert infrastructure or like a local libvirt instance or something, you wouldn't need any of this VXLAN tunnel stuff because by default you're going to be able to add any routes you want and kind of route traffic anywhere you want. So this part really depends on what type of infrastructure you're running on. So I'll just quickly point out how that part is configured. We actually, just in case anyone needs to go looking for this one day, we actually make use of a function from devstack-gate. So the folks in infra had written this functionality for devstack multinode jobs, and we just kind of piggyback off of that and reuse their code. So there's a function in devstack-gate called OBS VXLAN Bridge. You pass this thing like some local IP address and remote IP addresses, and it's going to SSH to all the nodes and set up Open vSwitch and set up all the VXLAN tunnels and whatnot. This actually works really well for our purposes. So yeah, I think that's it for CI now. Any questions about that or anything? Okay. All right, so I wanted to kind of show what we did in Okada to kind of make this more useful for end user consumption, because it can be a little bit difficult to kind of set up outside of CI. So one of the things that I worked on was adding this new resource directly to Heat, which is now called OS Heat Deployed Server. So you can actually make use of this directly now instead of having to map your OS Nova server resource to a new nested stack type. And this also allowed us to stop using admin credentials everywhere. So in that example I just showed from that CI job setup, you could see that that URL I was actually curling. That was actually a Swift temporary URL that's going to expire after a certain amount of time, and it's specific to my Keystone tenant that I was using at the time. So before we were able to do that, we actually had to hard code like the admin username and password like directly on each agent configuration, which is obviously not ideal. You don't want your overcloud nodes to have admin credentials to your undercloud. But since we were just using it for CI at the time, it wasn't really that big of a deal. So, this is one of the things that we kind of added in Okada to make this easier to use. So now the deployed server template that we have, it's actually a direct OS Heat deployed server resource. And so, we're able to associate deployments like directly with this resource instead of kind of having to use the dummy software config resource that we were using previously. We also added to show how this is set up. So out in the TripleO docs repository, we have a fair amount of documentation now on how to set this up for an actual deployment. It's out here under feature configuration. So if you're interested in trying to kind of give this a try for your own development, I would kind of suggest reading through this and kind of understanding how to set this up. Some of the things you have to think about when you're setting this up is, not all your nodes are going to be connected to your provisioning network by default. So that was kind of a pre-existing requirement whenever you used TripleO previously was, all of your overcloud nodes have to be connected to the same provisioning network so that, we can do Pixie on that network and have the HCP requests flow back to the undercloud and things like that. And so obviously they're going to be getting an IP address that's going to give them a route directly to the undercloud. Well, if you're not actually provisioning your nodes, then there's no need to have that requirement. So one of the big things when using this feature is that you can configure your undercloud so that Heat is listening on the public endpoints. So that way you can kind of hit those endpoints from any network. Also, I talk a little bit in here about setting up SSL, and this allows you to bind the undercloud services, the API services, to IP addresses that are not on the provisioning network. So this is actually the default way that you need to set things up to use the UI as well, because if you want to use the UI like from your laptop or something, obviously you don't want to have to be connected to the provisioning network to talk to those APIs. So this is the same way that we get around that problem. Is we set up SSL that's actually bound to a host name, and then you can assign that host name to any IP address. And the same for here as well. Your overcloud nodes can then talk to that host name instead of having to talk to an IP address that's on the provisioning network. And now, obviously, whatever network your overcloud nodes are on, they're going to need a route to that host name, which, there's no magic here, and your networks still have to be connected somehow. They just don't have to be the same network, but you do need a route between them. In this section, I talk a little bit about configuring your overcloud nodes and kind of testing the connectivity initially. It's a good idea to do that kind of before you get into a deployment and then realize that you don't have connectivity back to the undercloud. It's kind of a pain to kind of have to start over at that point. So that's why I added this part. Down here is where I have, I just talk about the initial package installation. So this part here kind of maps back to that Bootstrap or Bootstrap overcloud full, I think the script was called, where we just install the Heat agents on each subnode. And really, if you're starting, we've tested this with just a vanilla base CentOS image. I've also tested it with just like a vanilla CentOS installation or minimal CentOS installation from kickstart, and this is really all you have to do. You just have to install this heat agent, and then your nodes are basically ready to go once you configure the agent later on. As far as actually using this feature, when you go to deploy the overcloud, you have to pass that environment file that I showed earlier. And then there's another environment file as well, which does what I kind of call secondary bootstrap. As long as you have the agent installed, at that point, you can run arbitrary scripts on the node. So all the rest of the bootstrap stuff, which is really just installing some additional packages like OS netconfig and Open vSwitch and things like that, that's all self-contained within TripleO heat template. So we don't have to document that as manual steps. Let me just show that real quick, what that looks like. So we have a nested stack here that just runs this script. So we install some additional packages, Puppet modules, OS netconfig. I've got the agent listed here, but it's already installed if this script is running. I just listed for verbose sakeness. OpenStack SELinux is actually not installed by default, and no OpenStack packages require it, which is a little weird. So we have to install that manually. TripleO, we expect our Puppet modules to be symlinked under etc Puppet modules. For CentOS, we then disable SELinux, and then we have to reset IP tables as well. So it's pretty short, but these still are some additional manual things that we have to do to each node. Not manual, but kind of before we start deploying the OpenStack services. And then I've got some custom roles here as well. And the custom roles, that does is earlier I talked about the heat constraints for the glance image, and there are also constraints for like Nova flavors as well. So if you pass in a flavor name to heat and say, hey, boot me an instance with this flavor, it's going to verify that flavor exists. Well, we're not actually booting any instances, but our templates are structured in a way that it's still validating that the flavors exist. So we added this little part to our roles file called disable constraints, which is just a Boolean. And if you set that to true, then what's going to happen is when your templates get rendered by Jinja, we look at the Jinja 2 template for the overcloud. If I can find it here, let's see. Is it in this file? Might not be in here. Let's look in one of the role. Actually, let's look in the role template for the custom roles. Here we go. Here we go. So we have a little bit of Jinja logic here. So if disable constraints is not defined, then go ahead and add a constraint on this heat resource that says, hey, this value here must be a Nova flavor. So we're setting disable constraints to true. So these two lines are actually going to get left out of the heat template that's generated from this Jinja template. So that's why we have to use custom roles files when doing this. Previously, before we had that support, we were just creating all those dummy resources, which is why we were creating the empty image and loading that into Glance, and we had to make sure all the Nova flavors were created, even though we weren't actually using them. I just talk a little bit about the network configuration here. The deployed server port map is a way you can assign IP addresses, static IP addresses, to nodes that aren't going to be able to get DHCP from the control plane network. Running out of time a little bit, so I'm going to kind of skip over the rest of that because I kind of wanted to show kind of the next steps about where I was going with some of this stuff. So kind of what I've been working on recently is kind of this concept of split stack, which is this idea of deploying 2 stacks in TripleO by default. So we deploy one bare metal stack, and then we deploy a second services stack. And then we use the deployed server feature to kind of tie the 2 stacks together. So even though we are using Nova and Ironic in the overcloud bare metal stack to create our initial nodes, like running a CentOS OS, the second stack, the services stack, doesn't actually have any knowledge of that. Those nodes could have been deployed by any means. It just happens to have been deployed by Nova. And so the reason this is kind of appealing to some folks is you can kind of manage these stacks separately. It makes things kind of more modular and pluggable. And if something happens to your services stack, you're not going to destroy all your bare metal nodes because they've actually been deployed completely separately from that stack. So I kind of wanted to show how that worked. Sorry to kind of jump to the end here. So I've got a little script I've been using just called deploy bare metal. What I'm going to do is just kind of grab the overcloud deployment command out of that and run that. So I'm going to call this stack overcloud bare metal and run that command. Didn't work. Because my variable wasn't quoted, so I'll just fix that. All right, so we've got the deployment started now. One of the things that I've been working on in Pike, you'll see that I passed this deployment Swift data environment. So what that does, I just switched over to a new terminal here on the same undercloud. If you look at that environment, this is actually passing a new parameter called deployment Swift data map. And this is a map of host names to a Swift container and Swift object. So what this is going to allow you to do is it's going to allow you to tell Heat what Swift container and object to use for storing the metadata for each node. So at the very beginning, when I showed kind of querying Heat for that metadata URL and how that's kind of a pretty unfriendly process, it'd be better if instead of using a random value for that, we could tell Heat an exact value that we wanted to use for each node. And then kind of once you know that, you could integrate those known values with like Cobbler system profiles or something. So that way, when you provision these nodes, they're going to automatically be assigned with the right agent configuration. It basically skips that whole step. So if we look at what Swift containers have been created, we've actually already got a few out there. Those might be from a previous deployment. Oh no, they're probably from this deployment here. We can see that I've got a container called overcloud compute and overcloud controller, which correspond to that parameter value. And I can actually list those. And in here, I have an object called 0. And it kind of corresponds to this overcloud controller. And use an object called 0. And if I wanted to download that, just to kind of show you how this data is stored in Swift. Now I have a file in this directory called 0. Not really a great name, but for demo purposes, it's fine. And right now, the only thing that's in here is just the agent configuration because we haven't actually got to any deployments yet. You can see the Swift temporary URL for this object is this auth part is just your tenant ID. So that's going to be a known value. And then we have the container name here, overclock controller. And then we have the object name. And then we have a temp URL signature. This is going to be a unique value, so you're not going to know that ahead of time. However, you can generate your own Swift temp URLs for these objects and then go ahead and embed those into your deployed servers. So we don't actually have to use the exact same temp URL. As long as we're pulling the same object, we're going to get the same data. So that's kind of the mechanism of how you'd be able to set all this up beforehand without having to wait for Heat to do it and then manually query Heat to see what these URLs actually are. You can kind of do it all beforehand. Look at this stack. The other thing that this stack is doing is passed to the overclock bare metal environment. This is actually a Jinja 2 template. And one of the things that this does is for each role, it deploys an empty list of services. So it's not going to deploy any services on that role since I just want a bare metal stack. And I also map some other resources to none, but most significantly, it's the post-deploy steps. So it's not going to run any Puppet on the nodes. It's just going to deploy the bare metal OS. This should be about done. This is actually going to runs in about 10 minutes because we're not actually deploying any services. But the only other thing I wanted to show was just kind of deploying the services stack next. It's a real similar command, except we pass all those deployed server environments. And there's also a new stack output on the stack, which actually it generates an environment for you that you can pass to your services stack so that you don't have to write that part manually. May or may not be available yet before the stack actually finishes. But I just called it deployed server environment. So let's see if the value is created yet. No, not yet. Yeah, probably won't be available until the stack's totally complete, but it's getting close. But that's just a convenience, really, so that you don't have to go look at what ports were allocated, because obviously you want to be able to reuse the same IP addresses that the nodes already have. So you don't have to write this environment file and look at those values yourself. Let's see again if it's available. Any questions or anything about this? No, we're getting close to the end. Okay. Well, you can see in this output here, this is actually the contents of an environment file that you can write to disk and send directly to the overclock services stack. So one of the outputs is actually the contents of that environment that I passed in. If you hadn't done that for the first stack and let Heat generate those from random UUIDs, this would actually tell you what those values are ahead of time that you can then pass to the services stack. So I have a little script to deploy the services stack as well. So this command here is just going to read that stack output that I just showed. It's going to write it to this JSON file, which I'm then going to use to call this one over cloud services. And this is the command I want. And now that's going to deploy. Let's see what happened there. A stack there. That's going to deploy the services stack using the deployed server feature, and it's going to make use of the servers from the previous bare metal stack. So yeah, that's pretty much it. If we wanted to SSH to any of these nodes, we could actually see them start to pull down the configuration for the overcloud services stack once it gets to that point. So if we SSH to one of these nodes, first I'll just show the agent configuration here. So you can see, based on that parameter value where I said use a container name called overcloud controller and an object name called 0. So you can see indeed that is what's being used in this Swift temp URL. We haven't gotten to any new metadata yet, but we will eventually. That was pretty much it for what I wanted to show. All this stuff that I showed here at the end is just posted as patches right now, so obviously it's subject to change, but you know, that's kind of where I saw some of this stuff going. All right. Any questions before we wrap up, or anything you want me to? And if you give this a try, let me know how it goes. Be happy to help. Talk to everyone later.
Thanks, James. Cheers.
Thanks, James. Bye.